Hi, everybody. We're going to start module 3, and that's Fourier series. As usual, I'd like to start any module by the application and why we are learning that before we will start the math issue. Well, so that's, the topic we're going to discuss in this module. We're going to discuss why do we need Fourier transform or Fourier series, and we're going to take two forms of Fourier series, one in trigonometric form and one exponential form, and then in the end we'll have line spectra. Of course, in the middle of the module, we're going to learn how to use Matlab to represent Fourier series. So now I'm sure everybody asking, what is Fourier series? Well, first, do we need to learn about Fourier series as electrical engineer or mechanical engineer? Yes, we need. Of course. We need to analyze the electric circuit and to study electronics, signal processing, and other many applications. Well, let me give you one example. In this circuit, we have linear two-port electric circuit or electric system. And as you see here, we have like the input has impedance, ZS, that's the impedance of the source. And we have like voltage source or current source. And this source is sinusoidal. Or maybe you can have DC. That's what we used to. And then we have at the output port, we have the load impedance. And usually, when we analyze the circuit or we design the circuit, we start to represent the system by differential equation, and then we apply the input, which is sinusoidal wave, and then we get the output, another sinusoidal wave, different magnitude, different phase shift, and it's done. Well, that's what we learn, but not all electric circuit has input sine wave or DC. Not all circuit have like that. For example, in this electric circuit, the input is like, you can say sawtooth waveform. That's maybe you can have a square wave or triangular wave or different waveform, not different than sine wave, different than DC. So what we're going to do, how can we analyze the circuit? And we only know how to use or how to analyze the electric circuit when the input is DC or sinusoidal. Well, Fourier series has the answer. Source like that, it can be decomposed into a series of sinusoidal wave, as you see here to the right. Any periodic function, any periodic signal can be expressed as a series of sine wave with different frequencies. The first one, usually, we call it the fundamental component. Let's say that the frequency is equal 60 hertz, for example. That will be our first one, the fundamental component. And then you have series of harmonics. What does mean harmonics? It means if you look at this one, the second one, during the same period of time that the fundamental component already there, you'll find you have one cycle, two cycle, three cycles. So the frequency is like, 3 times. So that will be the third component, the third harmonic. Because the frequency of this one is like, 3 times the frequency of this one. And then when you count this, maybe you find this is the fifth, seventh. So the harmonics, they have multiple frequencies of the fundamental component. But when you add these components, it will give you this one. Now you may ask, so what when you decompose this input source, which is not sinusoidal, into series sinusoidal? No, it's good. Remember, we assume that this network or this electric circuit is linear. So you take this as an input and you find the output. And you take the second one as input and you find the output. The third, the fourth, and so on. So you have a series of input, and every time you analyze your circuit, you get the corresponding output, and in the end, you add all of them using superposition. And as you know, superposition can only be implemented for linear network. And we assume from the beginning linear network. So that's an application. And that's very important in analyzing electric circuit and electronics. So what's harmonic? Already I start in the previous slide to tell you what harmonic. When you have non-sinusoidal current or non-sinusoidal fault, you see it's distortion here. It's not pure sinusoidal. This one that's the effect of harmonics. It means there are some components that have frequencies multiple of the fundamental, the harmonics. And these harmonics that has high frequency, harmful for the equipment, electric equipment. Yes, because overheating, it decreases the lifetime of the equipment that we are using. So simply it really, it causes severe harm for the electric equipment. So what we're supposed to do? Using Fourier series, it can tell you the harmonics component, then you can design filter to get rid of them. So that's another application, right? I'm showing here in this, when you read this slide, I'm showing here, some components of the harmonic that can be, solved using a filter. Now, let's just go backward. In this example, as you see here, let's just make it bigger. We have three components, x1, x3, x5. And the first one has a magnitude A1, peak value A1, and the frequency omega 1. And you know, of course, how you get omega. Omega is equal to pi f. So omega is the angular frequency of the frequency. Let's say, for example, this frequency is equal to 60 hertz. So, and we have another component, x3. It has another amplitude A3. It has frequency 3 omega 1. It means the frequency of this component x3 3 times the frequency of the fundamental component. It means that will be like 180 hertz. And then another component, x5, it has 5 times the frequency of the fundamentals. Will be 5 times 60. That will be equal to 300. So we have 3 components. And what we want to do, want to add them and see what we'll get. It's a backwards. All right. So let's see what we'll do. And we are going to use Matlab. So this time I'm going to review with you how to do the Matlab. I have the program here and I run it, and I advise you any Matlab in this handout, you should try it by yourself. Rewrite it again and make sure that you get the right answer that in front of you. Well, now let's just see how we can write the program. First of all, when you write in a program, use these 2 things, clear and CLF. Clear, so to clear your memory for any calculation before, so it doesn't mess up any new calculation you're doing. And CLF to clear any figure, the handles of the figure, so every time you refresh your figure will not be dependent on the previous one. Always just do that before anything. Of course, you make the comment to mind yourself, what are you doing in this code? The first line here, I put A1 and A3 and A5. These are the amplitude of the sinusoidal wave for X1 and X2 and X3 and X5. So A1 is 90, A3 is 30, and A5 is 5. And that's known, the all harmonics has frequency more multiple of the fundamental frequency, but the amplitude always less than the amplitude of the fundamental component. So the amplitude of the fundamental is equal 90, of the third is equal 30, and the fifth is equal 5. Let's say volts, for example. The frequency F1 is the fundamental component for the X1, and we assume it equals 60. So F3, I just multiplied by 3 times F1, I get F3, and so F5. So now that was the second step. Third step, I get the period of each component. And you know the relationship that the period is equal 1 over F. That's what I did here. T1 is equal 1 over F1, T2, and just very simple. Nothing till now. It's just I am translating the whole algebraic equation into Matlab code. Now I'm trying to find omega, the angular frequency, and we know that omega is equal to pi f. So omega 1 is equal to pi f1, omega 3, and so on. All right. Now that's TS, the time step. What does mean time step? And when you are doing the simulation using Matlab, the calculation should be done for each time step. So I choose here the time steps T5 over 20. Let me tell you why I did that. As you know, that if you go back to the slide that has harmonic, first one, okay. That is the first, then the third, that's the fifth. So you observe the time period of the fifth, this one, the smallest one. The fundamental has big period. And you want to divide it. So it's better to divide it according to the smallest period to make sure every single component you have, you divide it into many samples. So when you take the calculation, you get almost exact. That's why I use the smallest period, which is in this example was T5. Because I mean, it will be 5 times. All right. The frequency to 5 times, and the period will be 1/5. So that's very small. I divide it by 20. It means, I mean, this is small one for the fifth, I divide by 20. So each one like 10, so you have 20 points you do calculation. That's time step, T5 or 20. All right. Some people, you know, say it's equal 0.01, but I mean, when you put absolute number, it should make sense, you know. So it depends on what the period of the component that you want to simulate. So that's the time step. Now, that's the simulation. It starts from initial time to the final time. Here, I mean, take like 3 cycles. 1, 2, 3. That's one period. 2, 3. So you want the result to cover 3 cycles. You will ask which one is the fundamental component, the third, the fifth. Of course, you wanna take the biggest period. That will be the fundamental. So the final time starts from T initial, that will be 0, and the time final after T cycle. If each one is equal T, and this is the fundamental, so the final time will take 3 times this period. You will not take the small one. The small one, you take it to slice, but the big one, that's your result should be shown over 3 periods of the fundamental component. So T is equal from T naught to TF, and in the middle you put the step, and already did the step, right? And this is the TF3, T1 here in this step. The final time is equal to 3 T1. All right. All this we are preparing for simulation. Now you just write the equation for the voltage. V1 is equal A1 sine omega 1t, and you already did omega here. It's calculated before. Make sure when you write any expression and you use any variable, this variable should be defined before this line. The same thing, the equation for V3, for V5. All right. And here you have V total. V total is equal V1 plus V3. Now we are ready. You can sketch between the voltage and the time. All right. But now we need something else. We need to plot the spectrum, the magnitude spectrum of the signal. What does it mean, spectrum? That's another definition. It means we have, how many components do we have? We have 3 components, right? We have the first, the third, the fifth. Let me just show that. We have the first, the third, the fifth. And this one has 60 hertz. And this one has 3 times, that's 180 hertz. And the fifth will be 5 times 60 will be 300 hertz. That's the frequency. The amplitude is given. The amplitude here is 90. A1 is 90, and this one is 30, and the other one is 5. It's a simple one because there's the first example. The spectrum line, I mean, it's like the relationship between the frequency and the amplitude. That's for the magnitude. But when you hear the word spectrum line, it means you want the relationship between the frequency and the amplitude, and frequency and the phase. What does it mean, phase? Well, any sinusoidal voltage has magnitude and phase. Give us an example. Okay, let's say that the voltage is equal 100 sine, and omega is equal to pi f, and f is equal 60 plus 30 degree, for example. So the magnitude is 100, and the phase shift is equal 30 degrees. And you can change it to radian, usually use the radian. And all this happen at this frequency, 60 hertz. So at 60, you're going to make 100, and at 60, you're going to make the 30 degrees. That's the line spectrum. But if you have many components, so you have to put all of them on one graph, so you can compare between them. All right. So now we want to sketch the spectrum, so you have to define the range. You're not plotting the curve with time. No, you are plotting the curve with frequencies. So you got to define the range of frequencies. So the frequency starts from 0, that's the initial, and the final, as you know, you have 60 times 5. Because we said we have the first one, F1 is equal 60 hertz. The third one is equal to 3 times, we have 180. And the fifth one is equal 5 times 6 is equal 300. So when you want to sketch, you want to leave just a space before and after, not just come on the edge. So I added another one, F6. However, it's 0, but I added just to have like space after you plot your curve, so it will be clear. So I multiply 6 times 6. I know it's 0, but just leave space. Nice, you know, not to come on the edge. Now, I define W, the length of the frequency vector. What's frequency vector? Well, the frequency starts from 0 up to 6 times 6 means up to 3600 hertz, and the step every 60 hertz. I don't want to make the sampling really small like the time domain. Why? Because I have components at definite frequencies, and I know all of them multiple of the fundamental, and the fundamental component is 60 hertz. So why I'm going to make a lot of them? It's just enough at each 60. Each 60, I will see the amplitude of each harmonic component. So that's why I don't make it like the time. So I want to know the length of the vector. What means the length of the vector? It means how many components. Well, I can tell you now. You start by 0, 60, 120. You add 60 every time. All right, 120, 180, and then till you reach 360. So how many elements in the vector? So you want to measure how many elements are there? 4, 5, 6, whatever. Why? Because you are going to first define another vector, and you want to put everything zeros before you start to update the values of each amplitude. So you want zeros, but you want to know how many zeros. How many zeros? In Matlab, you should match the same number of elements of the vector of the input like the output, because I'm going to sketch the amplitude against frequencies. All right? So Matlab will give you error if you have two vectors you want to sketch them together, because in the end you will say you want to plot A against F. So both they should have the same length. So that's why I found W equal length F, and then I say A is equal zeros 1 W. What does it mean? It's going to be like a row. 1, it means the number of rows. So you have only one row, and W. Assume that W is has 9 elements. So that's the first element. 1, 2, 3, 4, 5, 6, 7, 8, 9. And this one will be 9, for example. So they are matching. So when you make the plot, Matlab will be okay. Now, I did zeros for every single thing. Now I will start to look where the components of the harmonic. I have here A of 2. Now we'll say, why say A of 2? Because A, we agree with it, a vector, row vector here. When you say A2, it means the second element equal A1. Now, see, you are confusing us. Why you put A2 second element? I will tell you why. I start from frequency 0. So this one corresponding to frequency 0. I don't have anything at 0. I start from frequency equal to 60. So the 60 is here in the second element, and I know the amplitude of it. So yes, you know the amplitude. The 60 hertz has amplitude equal A1, and A1 is equal to 90. So I know it's equal 90. It's A1. So I say here, the A2, it means in the second place, put A1. It's the amplitude of the component that has frequency equal to 60 hertz. Now let's think about it. What's the following one? We have the first fundamental, and we have the third. And the third, 3 times 60, 180. So now you have the first frequency, you start with 0, 60. Add another 60, 120, another 60, 180, right? And you continue. That's the first element. That's the second element. Already did it. Second element. That's the third. That's the fourth. Why? That's 3F1. So that will be the location of A3. I'm sorry, the A4 corresponding to the third harmonic. 1, 2, 3, 4. As a row, this is the fourth element in the row vector A. That's row vector A. And where are going to put here? What information? The amplitude of the component that has frequency equal to 180, which is the third harmonic. What is the amplitude? It's A3. And it's given. A3 is given. A3 is given here, equal 30. And then after that, the fifth one, A5. When the frequency 5 times the fundamental, the amplitude is equal 5. We call it A5. You go there, you look which one will be 5. You'll find that's equal to this. It's the sixth element because because we start with 0, so 0 is not count. So you add 1. That's in general. So at the sixth place in the vector A, you put A5, which is the amplitude of the fifth harmonic given. Now you are done. You have two plots. That's the time with the voltage. You get it from this equation that we did in the previous page. There's the voltage and there's the time. You're going to use, there's the time and there's the voltage. You are going to plot V against T. Let's see what you did. Yes, here, T, the x-axis, V, the y-axis. The second plot will be the frequency. You have here the frequency, yes, and with A, right? A. So you'll find here frequency and A. And you don't use the word plot, stem, because you are not going to draw like a continuous curve and a curve. No, you are going just to put the values of A's at specific instant. So you use the word stem. Stem is used to plot discrete curves, discrete graphs, all right? So stem, frequency is x-axis, A, the amplitude, all right? And both, they have the same length. We agree about that. Since we are going to divide the screen of Matlab into two, you want to sketch them in the same screen, so I divide the screen like that. So how many rows? 2 rows. You say subplot 2, that's 2 rows. 1 column, they are on top of each other, 1 column, 1 column. And this will be screen number 1, that's screen number 2. So you will say subplot 2, 1, 1. It means you have 2 rows, 1 column, and this is the first screen. You are going to put T against V. You go subplot 2 rows, 1 column, you are on the second screen, you sketch the frequency against A. And that will be, that's it, and that's what you got. Look what happened here. I added 3 components. What you got? You got waveform, not pure sinusoidal. What does it prove? It proves when you see any waveform like that, it means it consists of sinusoidal waves of different frequencies. It consists of fundamental component plus harmonic. And here, the spectrum line shows you the amplitude of each harmonic component and at each frequency. Here you'll find you have line here, it's at 60, your fundamental component, and you look at the amplitude is 90. So you know that the fundamental component has 90. And you have here one at 180 at the third harmonic, and you see the amplitude, 30. And what you have here at the fifth, small one here above 0, a little bit, 5. So you know the size of the harmonics. So when you want to design a filter, you know what the values of the elements used in the filter according to the amplitude of each harmonic element. So do you agree with me that Fourier series? But somebody will say, wait a minute, you didn't explain Fourier series, you add the 3 of them. Exactly. I didn't explain Fourier series. But what I explained to you, that any waveform doesn't look like sinusoidal, you expect it can be decomposed or expressed in a series of sinusoidal. So in Fourier series, For next lecture, I'm going to get waveform similar to this one, and I don't know what's inside it, and I will get you series of sinusoidal wave that makes this waveform. All right, that's it. Introduction. I hope I understood the importance of Fourier series.